Okay, so before we dive into what we did in Cambrian-S, we have to start from a more broader perspective. So I think during the past 10 years or maybe 50 years, we observe a very significant and very significant change in computer vision field. It's shifting, the whole field is shifting from the controlled and intermediate task to real-world task. For example, maybe 10 years ago, we studied ImageNet and we study how can we design the network and so that we can train one image classifier that perform better than human on the ImageNet classification challenge. And after that, we study more high-level tasks like the object detection or segmentation or panoptic segmentation or video segmentation. These tasks are more structured visual understanding tasks. But with the as a high-level visual task, it's also more ambiguous than the previous classification one. And also now, after the ChatGPT, after we enter into the ChatGPT era, now we focus on the video or image question answering. So this kind of visual question answering task are more close to the real world scenarios, but it also introduces a lot of the bias or shortcut. So here's the background. But from the, as we know, okay, we are trying to shift from the control task to the real world task. So what's your imagination of the real world task of visual understanding? So I think different people will have different, totally different answer for this question. But from our opinion, our definition or our imagination of the ultimate real world real task, there are several characteristics. So the first one is the ultimate real-world visual task has to be video-related. And why we want it to be video-related is because video represents how humans' visual system works, right? So as a human, okay, we every day we will perceive a lot of the visual streams. It's not a frame by frame. It's not image by image. It's a video. So video is essentially how our visual system works. And video is the entanglement of semantics, 3D space, and time. So if we look at one certain frame, we can say, okay, there is some objects or something is happening. So it's basically semantic information. And if we look at a sequence of video or a clip of video, then okay, we will say the video is happening inside some 3D space. And the video is about time. And besides the video, so we also want the real-world video task be related to infinite long video understanding. And why we want it to be infinite long. Humans can perceive lifelong videos, right? So as a human, we can remember not everything, but a lot of things from our childhood to our college to after being a computer vision researcher. And we also can efficiently recall maybe 10 years ago information. For example, maybe you can still remember what's your favorite course when you are in your primary school, or what's your favorite sports when you are in the college. But for current video multimodal language models, they often fail on hour-long videos. So to study this, or to realize our imagination of the real-world visual task, so we define the supersensing here. And here is the following is how we hierarchy our supersensing. So we hierarchy the supersensing in 5 levels. It starts from linguistic only understanding. So For linguistic only understanding, it means there is no multimodal intelligence, it's language only. Its reasoning is only confined into text and symbols without the sensory grounding. So current multimodal language models, so it's essentially language models, right? But current multimodal models have already progressed beyond this stage. So here are some examples of the linguistic only understanding, like the ChatGPT or the Gemini chatbot. And the second level is about semantic perception. So it's about naming and describe things for user prompts. So here, the model will have to parse in the pixels into objects, attributions, or relationships. This corresponds to the show and tell capabilities in current multimodal large language models. And here are other examples for this semantic perception, like how we chat with ChatGPT or Gemini with some visual inputs. And the third level here is we call it streaming event cognition. So the streaming event here is different from the static semantic perception from the temporal level. So here we want the model can perform always-on sensing for open-ended streams and can build its own memory across time. Yeah. And yeah, this aligns with the efforts to make the multimodal large language model a real-time assistant. So one example for the streaming event cognition is the AI glass. For example, this is Google's AI glass, and this is Google's Gemini Live. They are all real-time understanding models. And the fourth level is about spatial cognition. So here we are not asking the model to just describe describe the content in every frame. Here we want the model to understand the underlying 3D space. So in this level, we want the model to understand the videos as a projections of 3D world. And to achieve this, an agent must know that what is present, where and how things relate to each other, and how configurations change over time. And today's video models remains limited here, and we will show you why it's limited later. So one example for this 3D spatial cognition is, so imagining when you want to shopping some furniture like a sofa for your house, and okay, you will, sorry, but you will not only directly mirror the size of your own apartment. But one thing humans can do is when human can imagination, okay, how does it look if this sofa is placed on my living room? So this is a human's internal spatial cognition. And the last level is predictive word modeling. So this one, we call it predictive word modeling. And we want the model to not only passively perceive the frames, but also anticipate the future frames with its own internal word models. So in this way, the model can use the expectations and surprise to organize the perceptions for memory and decision making. So this process mirrors humans' unconscious inference and is largely absent in current system. So maybe you will feel that predictive word modeling sounds a little bit not related to spatial supersensing, but actually, let's start from a different perspective. So let's start think about how humans' brain works so efficiently, but human brain is so powerful on processing the lifelong visual streams. So one answer might be one answer in the developmental psychology is the predictive word modeling or the predictive mind theory or unconscious inference of human brains can help human to allocate the attention or memory. So here is one example about how humans predict world modeling works. So when an athletics is playing the basketball or the baseball, the human is not just trying to capture the trajectory of the ball every second. However, the reason human is able to hit the ball is due to human has the capability to predict when and where the ball will go. So, in other words, the human's action is guided by human's prediction of the future. And also here is another two examples here. So let's just watch this video. So here, our expectations or our world models tell us, okay, this man just sitting into a sports car, right? But let's see what will happen. So here we can see after the time evolves, from a different perspective, we finally got the truth. So actually, the man is just playing some visual tricks. He never sit into the sports car, and this sports car is just a toy. But from this perspective, it looks like the man just sitting into the sports car. But here, the surprise emerges. And also, there are other studies in the developmental psychology that studies how humans predict world model forms during humans' infants. For example, the human infants can predict, okay, if the car is approaching the edge of the cube, then as the time goes on, the car should fall down, right? It shouldn't just go straight like this one. And also, if there is an obstacle ahead of the car should just stop. However, if the car just pass by the object, then there is some surprise. So this is our So this is our definition of the supersensing. It has 5 levels from the linguistic only understanding to semantic perception to the streaming event cognition to spatial cognition and ends with the predictive word modeling. And we can see at the low level, it's more task-driven. And here the task-driven means you have the question, and then your task is to answer the question. But on the higher level, it's more about word modeling, and word modeling is more about passive understanding. Yeah, so this is our definition and hierarchy of the supersensing. So in the following work, we will talk about what's the current stage of our evaluation and data and architecture for this supersensing task. And we found that all of this, evaluations or data or architecture, none of them are ready for build a real supersensing video models. And in the following, we will delve into details one by one. So the first question is, how can we benchmark spatial supersensing? Are existing benchmarks enough or not? So to answer this question, we deconstruct the existing video benchmarks. So we try the following 3 different evaluation protocols. The first one is multiple frames. So we choose a video models and evaluate it on a bunch of video benchmarks by just process 32 uniformly sampled frame and then feed the frames into the model. So this is a very standard video representation method. And then we also test about single frame. And the model will just take the middle frames, only one frame as input. And the last setup is we will convert the 32 frames to a set of captions by using the Gemini 2.0 Flash model. And then we will feed these captions into the model along with the question and ask the model to answer these questions. So here is all these results. So on the far left, here is the results of the one video model on this different video benchmarks across different setups. For example, the first one is multiple frames, and the second one is the performance on single frames, and the last one is captions. And here we choose the video MME equals gamma, video MMU, long video bench, tomato, and also a lot of other video benchmarks here. But we found what we found here is, so actually, if we pay attention to the difference between the if we pay attention to the performance difference between the multi-frame and blind, and also the multi-frame of chance, we can see a lot of the video benchmarks can already be answered from only blind answers. So one conclusion from our results is that most of video benchmarks focus on semantic and knowledge recall, like the video MME and equals gamma and video MMU. And these benchmarks can be well solved by providing only one frames or some textual knowledge. And why it can be solved in such way? So we find a very interesting observation here is, for example, here is the spatial understanding questions in video MME benchmark. And we can find that the question is about space. So the question is categorized as spatial question, but actually the question is about physics understanding, right? So why other objects are flying? It's because the moon is approaching the Earth. And which feature of the astronauts' equipment indicates they can move independently? It's because, so this kind of question can just answered by only one frame, so without the temporal dimension. And we also found that only a few benchmarks probe spatial sensing. So we found that currently for video MME equals gamma and video MMU and long video bench and tomato and wave bench, this I think this, and including the perception test, these 7 benchmarks almost focus on the semantic understanding, and only our video and VSI bench can be used to probe spatial sensing. So here we found that the evaluation is not ready for benchmark the supersensing. So we have to build the evaluation first. So here we build our a new benchmark called VSI-SUPER. It's a two-part and long horizon benchmark for supersensing. So let's see how we did it. So first, to make the video, to build a very long horizon video, we combine several video sequences with online questions and answers. And we build a very needle in the haystack style tasks, but we are trying our best to make it realistic and contextually grounded. And we design it to be resistant to brute force context expansion by concatenating sub-video clips into an arbitrary long video, so that we can emphasize the true spatial supersensing. So the first part of our benchmark is called VSI-SUPER recall. So this benchmark is designed for the long horizon spatial observation and recall. So we randomly sample one video from the VSI bench video and added several frames by inserting some novel objects. For example, in this video, we select these 4 frames and ask the Gemini image editing model to insert the teddy bears in this frame. And then we concatenate this edited video with other random sampled videos into an arbitrary long video. And we ask the model about the following question. So the question is about which of the following represents the order of the teddy bear appeared in the video. So the correct answer should be the teddy bear appeared first. The first time teddy bear appears is on top of the toilet, and the second time is inside the bathtub, and third time is is on the sink, and the last time is on the floor. So it's about the recall several key frames from a very long horizon observations. And the second part is VSI-SUPER count, and this task is designed to count certain objects inside a very long video. It's a continuous counting task under changing viewpoints and scenes. So, for example, we will concatenate a lot random sample different videos here, and every video will have some instance of some common instance. And we will ask, for example, here we will ask how many different chairs are there in this video. And in the first video, the ground truth is 3 because there are 3 chairs. And in the second video, the ground truth is 1. And in the last video, the ground truth is 16. So in total, after watching the whole video, the answer should be 20. And we also design its online streaming counterparts. So for the streaming questions, we will ask the question at any time. For example, at the end of the first video, the answer should be 3, and at the end of the second video, the answer should be 4. And also at the end of the last video, the answer should be same as the 20. And also to following a VSI bench, we use the mean relative accuracy as a metric. So after building our benchmark, we first tested how current commercial models like the Gemini 2.5 perform on our benchmark. Here we tested Gemini 2.5 on video MME, video MMU, VSI bench, and our newly introduced VSR and VSC task. And here we found that even Gemini models, it can perform pretty good on this video MME and video MMU on this kind of semantic or knowledge-focused video benchmarks. But it fails at spatial sensing and super sensing. For example, Gemini 2.5 Flash can only perform slightly over 40% on VSI bench, and on VSR 120 minutes version, it totally crashed. And even for the VSC task on 1 hour video, the counting performance is super low. And also, if we compare the ground truth distribution and the prediction distribution of Gemini model on VSC task, we can find that Gemini struggles with the counting task. So here, every point means the x-axis is the ground truth value, and the y-axis is Gemini's prediction. And we can find that Gemini's prediction is always confined in a certain range. For example, in this 10 minutes version, Gemini's prediction is always below 25. And in this 30 minutes version, Gemini's prediction can hardly go beyond the 50. And in this 1 hour video, it's also Gemini's prediction is also below the 15. So this means Gemini can. So this means the current multimodal models is really hard to with this kind of counting task, and scaling data and context length or model on the number of parameters alone fails to improve the generalization across different ground truths. So after we build our VSI-SUPER, we have our evaluation method to the supersensing, and now we will study data. So when we're talking about data, let's first revisit how data works in the language model field. So in the language model pre-training or post-training field, language model will be trained on top of the millions of trillions of tokens of the internet corpus from the Common Crawl or the GitHub code or Wikipedia or archive papers. So this is the blast of the internet, and the internet provides such a huge database for the language model to train. But if we focus on video models, especially the spatial supersensing models, we will find that spatial sensing data remains largely underexplored. For example, this is one of the quite popular benchmark developed by Yuan Han. And for this llama video dataset, we can find that most of these videos are from kinetics, Ego 4D. They are all activity related or conceptual related or semantic related. So it's hard to find any spatial related data for current video multimodal models. And also we can see this is the models and humans' performance on VSI bench. And even humans can perform super good on VSI bench, but current frontier models like Gemini 1.5 Pro can only approach over 55 accuracy on VSI bench. So this tells us the truth. The data is not ready for spatial supersensing. So to bridge this gap, in Cambrian-S, we built VSI-590K. And to answer the question, is spatial sensing just a data problem or not? So to build our VSI data, we collect the videos from a diverse range of video sources. For example, here we will use the unannotated web videos, and we also collect some synthetic videos and some annotated real videos. And after collecting this video data and with these annotations, we design this data pipeline. So for the unannotated videos, we will convert it to frames and then use some off-the-shelf models like the grounding Dino or VGT to convert it to generate some pseudo annotations for these unannotated videos. And for these annotated synthetic or real-world videos, we will extract its meta-informations like the object counts, object boxes, or room size. And then all these informations will be fed into the data generation pipeline and converted to some question answering pairs. And for the synthetic video, here is one of our group's work. It designed one synthetic environment built on top of the AI tool Thor, and then design the camera trajectory to capture the videos in the synthetic environment. Yeah, and this is the video source of our VSI data. So as you can see, we cover a lot of the different source from for the annotated real video, we sample from the S5E4 and ADT and also ScanNet series and also ARK-Sense. And for simulated data, this proxor is generated by this SIMS-V pipeline, and HyperSim also generated some simulated data. And we also curate some unannotated videos. And in total, we can collect around 600,000 QE pairs. And following VSI bench, we design our taxonomy from the different types. For example, our question answering pairs will be designed for the object size or the directions between the objects or the number of certain objects or the distance between objects or the appearance order of one object or several objects in the video. And this is a distribution of our data set. We group it following the categorization of VSI bench. We can group it into configuration task, which is related to the rooms, the space layout, and the measurement task is about the distance or absolute size of objects, and also spatial temporal task. And this is a distribution from the task perspective, from direction, distance, size, count, and appearance order. And after collecting this data, we conduct ablation studies and to see, okay, how much does this data contribute to the real spatial supersensing? So here, our baseline here is a video multimodal large language model, and we add this different source of video data from the to the baseline and fine-tune the baseline model on top of it and see what's the performance change, how the performance change. And we can see almost all of these different video sources contribute to the VSI bench performance. And also we can see the real world videos contribute the most, and also the simulated video contribute the least. But fortunately, all of this data can provide rich annotations for spatial understanding. And after designing the data, we started pre-training, and we found that pre-training is also quite important for building a good spatial understanding model. So here we choose different base models. So the first base model is just language models, and the second model is the image instruction tuned models like our Cambrian-1, and the third model is our Cambrian-1 model fine-tuned on top of some video instruction tuning data. And the last video models is our Cambrian-1 model fine-tuned on 3 million video data with more data. And we can see from A1 to A4, the performance on VSI bench, video MME, or ego schema, they are all increasing. And then we fine-tune these 4 models with the VSI data only or with the general video data. And here we find that with better base video performance, right, from A1 to V4, we can see after fine-tuning, the performance is also increasing. So this suggests that the quality of the pre-training also influences the post-training effectiveness. And if we compare the difference between the VSI only fine-tuning and the mixed data fine-tuning, and we can observe that on VSI bench, the VSI only fine-tuning is always perform better than mixed data fine-tuning, but the performance gap decreases a lot if the model scale up to 7 billion parameters. So mixed data training can help us to preserve the general video understanding capability. And after all these explorations, we design a 4-stage training pipeline and train our Cambrian-S. So Cambrian-S is a spatially grounded multimodal models, and we use a 4-stage training pipeline from the alignment. The first stage is alignment, and followed by the image instruction tuning, and followed by the video instruction tuning, and ends with the spatial video tuning. So after this 4th stage, we compare our Cambrian-S model with other models on a set of the video and image understanding benchmarks, and find and surprisingly our models performs quite good on these benchmarks, and especially for the VSI bench, our model can perform much better than previous models. And on some general video benchmarks, our model's performance is competitive. And also here is a detailed video VSI bench performance. And we can see Cambrian-S 7 billion model can get maybe around 70% accuracy on VSI bench, and even 0.5B can perform similar to Gemini 2.5 Pro. And also for the route planning task, which is an out of the distribution task of our training data, but our Cambrian-S 7 billion model can still perform good on route planning. It's comparable, it's outperforms the Gemini 1.5 Pro and comparable to the Gemini 2.5 Pro. But although it's performed very good on VSI bench and other video understanding or image understanding benchmarks, when we evaluate models on our proposed VSI-SUPER, we found the performance is decreased a lot. For example, here on the VSI-SUPER recall task, the performance just decreased to 0 if we feed the 1 hour video into the model. And for the VSI-SUPER counting task, the performance is all around 0. So this tells us scaling up the data can benefit the spatial sensing, and but only scaling data cannot solve this spatial supersensing. So finally, let's talk about the architecture. So this is a very typical image or video multimodal large language model framework. One image will be converted to, fed into the video encoder and the projector to be converted into a set of the video embeddings. And then language will also be tokenized to a set of tokens. And then the language model will take all of this as inputs and generate its own language response. But however, this data is still not ready for supersensing. So what makes spatial supersensing unique? As we said, for the supersensing task, we want it take the video as input, and we want it takes infinite long video as input. So supersensing means it takes infinite tokens in and infinite tokens out. It's a streaming model and can be always on. But however, I think current architectures like lava-style architectures is still not designed for this. This is quite different from, so current multimodal large language model is quite different from how human brain works. So for human brain, our visual stream is extremely high bandwidth. So every second we will perceive maybe over 24 frames. It's a very high throughput. And also from our retina to our brain, it's around 10 million bits per second, the information flow. But all sensory inputs, all these viewing inputs is around to 1 billion bits per second. So this is still much more exceed current multimodal models capability. But in our brain, the unconscious inference or the conscious awareness can only perform around 10 bits per second. So for our human brain, most of the data is filtered and compressed before reaching our perception or understanding hub. But how can human perceive this? How can human achieve this? So here we prototype our answer for this super sensing, and we call it predictive sensing. So here we slightly modified our stage 4, our stage 4, and we add one additional head on top of the current model architectures. We call it latent frame prediction head. And during training, we not only we train it on both the question answering task and also the next frame prediction task. And the next frame prediction target is the variant encoder's output. So we call it latent frame prediction, which means for the first frame, the supervision is the variant encoded second frame's feature, and for the second frame, the learning target is the third frame's variant features. And this is how we train our predictive sensing model. So in this way, we want to build the internal world model through such next frame prediction training. And in inference, we use this violation of expectation, or simply we can just call it surprise as a guidance on how can we allocate our computation or storage. So for example, here as the frame goes, for every frame, the model will extract its feature and feed it to the model, and the model will predict the next frame latent feature. And then when the next frame ground truth comes in, we will measure the difference or the surprise between the ground truth observation and the predicted latent features. And then we can use this surprise as a signal for future use. So here we provide two case studies on how we use this surprise to solve the VSI-SUPER task. And the first case one is we use the surprise to build a memory management system. So for infinite long video input, we know that it requires the memory system to process such infinite long video. And memory is always built for store some useful informations and delete or duplicate unused informations or retrieve some useful informations when being queried. So here, so one of the key problems for such a memory system is how can we decide what to keep and what to discard? So it has to define. We have to make sure the memories in our memory bank is useful for future tasks. So here our solution is we can use the surprise. So the surprise here we can also say is a high entropy or unpredictability of every frame. We can use this surprise information as a signal, and more higher surprise score means this frame or this information may be more important for future use. So here is how we build our memory system. So yeah, this is a flow chart of our memory system. So here is the frames, and we use a sliding window attention for the frames. And so basically, we use the KV cache as memory. So, which means we will feed the frame into the language model and use the KV cache as a memory unit. And we also use a sliding window sensory memory help us to, which means only the frame can only attend to the previous frames within a certain local window. And also we maintain a very long-term memory here as a memory bank to store useful information. And also we design a memory consolidation function to help us to manage the budget of the long-term memory bank. And finally is the memory retrieval. So the retrieval here means once the user reads one question, and we will use the query as a key to retrieve the relevant memory units from the long-term memory bank. And this retrieved memory units will be fed to the language model and then be used to answer these questions. So the key design here is how we use the surprise. And we use the surprise score to compress or drop or merge these low surprise memories. So here, for example, for every frame that is being encoded, we calculate its surprise level, and then if this frame is not that surprised, then we will compress it because we believe less surprise means less information. And also, when we are our memory consolidation function is designed to drop or merge these low surprise memories. And this means, okay, once the long-term memory just exceeds its budget, then we can simply drop some memory units which has the latest surprise score, and then to keep our memory within a limited budget. So these are the results. We evaluate our memory framework on the VSI-SUPER recall task. So from left to right is the comparison between our framework and Gemini models, and also our models with memory or without memory, and we apply the prediction. We apply different surprise implementation. So let's delve into the detail. So first, we compare our results, Cambrian-S with memory, with Gemini 2.0 and Gemini 2.5 Flash. And we can see both these two frontier models, they just cannot process over 2 hours video. So the performance after 120 minutes is absolutely zero. But for Cambrian-S, because we have such a memory design and we can keep our memory in a limited budget, that means we can make sure our memory never goes beyond our context length. So the model's performance is very stable across different video durations. And also, compared to the without memory baseline, we can see with the memory system, the GPU memory usage is quite stable. It never, but if we do not apply the memory system after 2-hour video, the memory will go beyond the GPU limitation. And also, for the third figure, we compare our surprise implementation to a baseline. So here, our method use the prediction error as a surprise, but we take one easy way to measure the surprise is, okay, let's just measure the difference between the adjacent frames. So here we compare our predictive error as surprise with the adjacent frame feature difference as surprise, and we find, okay, across all video durations, our design can yield stable results. So in summary, surprise-driven memory system can help us to achieve better performance on VSR tasks than Gemini models, and also can help us to achieve consistent memory footprint. And the second case is how we use the surprise to solve the VSC task. And here we use surprise for the sense or events segmentation. So the key idea here is the surprise of humans, right? So humans also have a lot of, we also have a lot of surprise. And surprise also help us to organize our memory structures. Like, let's say the surprise can help us build the episode memory or build the structure of different event memory. So following the same idea, we design our surprise thing segmentation framework like this. So in general, it's a divide and conquer framework. It's designed for VSI super count task. So let's see how it works. So as the video goes, we will continuously calculate the surprise level, and if we find the surprise level goes beyond one certain threshold, then we will think, okay, we are entering to a new thing. We are entering into a new space. So we will use the previous memory to answer the question. For example, how many chairs have you seen in this video? And then we will save this answer in our memory budget. And after all videos are being processed, we will calculate the sum of all the answers as our final answer. So in summary, our key design here is we use the surprise for scene segmentation. And here, similarly, we also compare our model against the Gemini 1.5 and 2.5 flash model. And also, and we can see Gemini models, as the video durations goes longer, for example, for the 2-hour videos, Gemini's results are approaching almost zero. But however, if we apply our divide and conquer method, the performance is very stable around 14. We also compare the predictive error as a surprise with the adjacent frame vision feature difference as surprise, and we can see the performance is the advantage is super clear. And on the far right, we slightly modify our framework to adapt it to the streaming scenario. So streaming, as we said, streaming means, okay, the query can be raised at any time, not necessarily at the end of the video. So on this streaming VSC task, we can see there is also a huge advantage of our framework over the GPT real-time or Gemini Flash Live API. And if we compare the model's output distribution of our Cambrian-S model with the Gemini 2.5 Flash, and we can find that just like we said, every point here means the one prediction from the model, and the x-axis means the ground truth, and the y-axis means the predictions. So our expectations is so this gray line is our expectation. It's a perfect prediction. It means if the ground truth goes larger, the prediction also goes larger. But we can see for Gemini 2.5 Flash models, it's hard for Gemini model to do this. So Gemini's prediction is always confined in a limited range across all video durations. It's hard to predict the numbers over 50. But for our Cambrian-S with divide and conquer framework, we can see the model's prediction is much more better than Gemini models, and it scales well, along the number of ground truths. So in general, this divide and conquer framework help us. It can generalize well to larger ground truth numbers. So in summary, in this work, so first we define our hierarchy of supersensing. So we define 5 task levels from the linguistic understanding to spatial and word modeling and predictive word modeling. And then to evaluate the benchmark, we deconstruct existing benchmarks and find most of them focus on semantic and knowledge recall. And spatial reasoning and predictive word modeling are still underrepresented. So for the next step, to bridge the data gap, So to bridge the evaluation gap, we propose the VSI-SUPER. So VSI-SUPER is a 2-part benchmark for supersensing evaluation. And next step, to bridge the data gap, we create VSI-590K dataset and train our Cambrian-S models on top of it. And we observe very good performance of our Cambrian-S model on spatial reasoning and general video understanding. But we still observe the low performance on VSI-SUPER, which implies the data scaling only solution cannot solve supersensing tasks. And finally, we prototype the predictive sensing and prove its effectiveness on VSI-SUPER through 2 case studies. And the first one is how we use the surprise to manage the memory units. And the second one is how we use surprise for the sense annotation. So this is what we did in Cambrian-S model. And for future steps, I will talk about from 2 perspectives. The first perspective is spatial sensing. So for spatial sensing, we still observe great limitation of current models. So even our Cambrian-S model can perform good on VSI bench, but it doesn't mean it can generalize well to all spatial questions. So to improve current multimodal models' spatial understanding capability, we need better spatial representation, and also we need to shift from current passive supervised fine-tuning paradigm to active exploration and reinforcement learning paradigm. And also for the supersensing in video, as we said, for such an infinite long system, what to memorize and what to discard in our memory system is always a key question. So here, we should study passive predictive sensing like what we did in Cambrian-S, or proactive task-driven memory management. I think this is what people typically will do in current memory field. And also, its context. So another question for supersensing task is context-based memory enough or not? For example, humans, for us, we can learn from the high-quality data very quickly. So I believe it's also important for current multimodals to study test time training to learn from the past observations and which use the past observation to lower the future surprise. So this will be super useful for build some lifelong AI assistant. So all these details and resources are already available at the, here is our project page and website, or some training code or data and benchmark. So it's all available, and you can access it from our project page. And here is some related work to Cambrian-S, including the VSI debias work, and also SimSV work, and thinking in space, and Cambrian-1. If you can check it out if you are interested. Yeah, so that's all my presentation for our Cambrian-S work. And so thank you for listening.